Hello everyone, thanks for watching the video. I am very glad to give you a short presentation to introduce the paper Variational Progressive-Iterative Approximation for RBF-based Surface Reconstruction. Recently, with the wide use of 3D scanning technology, surface reconstruction from sampling points has become more and more important and has become a research hotspot, attracting many researchers. Many reconstruction technologies have been developed, which are widely used in robotics, computer-aided design, and manufacturing and other fields. In this paper, we design an RBF-based reconstruction method for points cloud reconstruction. This is our main goal for a given point cloud P with corresponding normal vectors set n. We shall reconstruct the surface S from fit to interpolate the given points. In addition, with the development of sampling equipment, a large-scaled point cloud fetching is easy for users, also it's challenging for mesh construction. Finally, points cloud with non-uniformly sampled, point clouds with missing data regions, and points cloud with noisy data could be very common for some scenes, sometimes it caused by the vibration of the equipment or the limitation of the viewing angle. Easy to find function that called radial basis function. The value of the function only relates to distance r. Let phi r or phi r divides rho is the function, where rho is truncated distance. Our choice is Wendland CS RBF. One advantage of the kernel is local support. It is a polynomial truncation function, r equals 0 when r greater than 1 and r equals 4 order 1 minus r times 4r plus 1 where r in the interval from 0 to 1. Another advantage of the kernel is that derivative at 1 is continuously differentiable, so the construction surface will also continuous. Radial basis functions based implicit methods have become a kind of popular reconstruction method, due to their capability of creating an object with complicated topology and geometry. The key step of RBF-based surface reconstruction is to solve linear equations. However, it is also the bottleneck of these methods. This is due to in the process of reconstruction, with the increase of data points, the linear system is prone to singularity, resulting in an unstable solving process and time-consuming calculation. In order to deal with this problem, a class of quasi-interpolation RBF-based surface reconstruction methods is proposed. However, as the quasi-interpolation methods still belong to approximate methods, they may smooth the detail features, and lead to large reconstruction errors especially in the sparse region of the sampling points. As the traditional method, we need to find an implicit function. For any pi in P, make fp equals 0. Easy to find that let fp equals to a linear combination of kernel function phi, where ci is parameter to be solved. But actually, the solution will be trivial solution. In order to avoid the trivial solution, L2 or L3 method was used. The idea is get the offset points of the given point along with the normal, i.e. let qi equals pi minus dni, where d is a small distance. And let fq equals -1. There are no non-trivial solution, but the size of system becomes 2n times 2n. Hermite variational implicit surface fitting was used for reconstruction. We know the define of the variational problem and the condition of them. H is a reproducing kernel Hilbert space with kernel function k. Thus, the size of the system become n times n again. In order to avoid solving the linear system, we designed a PIA method. From the iteration the result of this equation become from approximate to exact step by step. The image shows the convergence tense during the iteration. With the increase of iteration times the error is decreased from the top to bottom. The black dots are the value of point which need to reconstruction, and the line is the crave to fit them. When iterating 50 times, the line interoperates all the given points. The core idea is that, when using proper RBFs in our framework, it allows to simply transform the iterative matrix to be symmetrical and positive definite. This result contributes to reduce the computational cost greatly and produce high-quality reconstruction results. Finally, plenty of numerical experiments on various challenging data are presented to demonstrate the efficiency and effectiveness of the proposed method, and the superiority to other similar methods. For any point x belongs to R2 or R3, let us define a function fx to fit or interoperate the original points and their normal. First, let us define the function about the position. Let upper phi x equals phi r, divide sigma j phi r. It means normalized radial basis function. The reason to divide all radial basis function in its neighborhood is to remove the effect of the density of points. Second, in order to measure the error of its normal vector, we use the sum of the inner product to calculate the error. The rho phi ix means the gradient of the surface. As phi x is an implicit function, it's the normal vector of phi x. So, combine the two objects, we can get AF, input every pi into formulate B and get a set of linear equations, where Ci are coefficients to be calculated. Let upper Bij equals phi ipj and let lower bj equals negative the sum of ni dot the gradient of phi ipj. Thus, we can write it on matrix forms. Upper bc equals b, where c is the set of ci, and c equals the inverse of upper b dot b. The progressive iterative algorithm is equivalent to Richardson iteration in solving linear system. In fact, in order to solving the system BC equals D, we can use a iteration method CK plus 1 equals CK plus B minus upper B CK. Because the spectral radius of I minus B less than 1, so the limitation of nth order of I minus B tends to 0, so that sigma I minus B will tends to the inverse of upper B. By iterate the C0, C1, C2 to CK, it will tend to inverse of upper B dot B. We also can prove the convergence of its error. Let error ek equal ck minus c, where c is the exact solution. Thus, the norm of ek plus 1 equals the norm of I minus b times ek. And as we all know, the norm of matrix vector product is less than the norm of matrix multiplied by the norm of vector. So the error ek plus 1 will less than the ek, and tends to 0 by the power of norm of I minus b. When the norm of residual error tends to be 0 during the iterative process. This property is also called PIA, as the sequence of the generated curves or surfaces will finally converge to the given point set P, i.e. with the iteration times k tends to INF, the implicit function of Pi will finally tends to 0. This is the way to reconstruction surface from fitting to interpolation. A new way to solve the problem is that we find by matrix splitting, the matrix B could split into two matrix C and D. Remember the define of matrix B. It's the normalized RBF, let C equals the normalized parameter, and D is a sparse symmetric positive definite matrix. Thus, upper Bx equals B is equivalent to Dx equals inverse C dot B. Assuming that there is a set of conjugate orthogonal bases Qi in the multivariate space, then Qi.dqj equals 0 when I is not equal to j. As shown in the image, if Qi/Qj is conjugate orthogonal in Fig A, it will be orthogonal in the resized Fig B. Thus, let C equals alpha I Qi, where alpha I is need to be solved. It's equivalent to change the basis, from solving Ci to solving alpha I. Since solving C is equivalent to solving an optimization problem, Also, solving alpha is also equivalent to solving an optimization problem as shown. But the QI/QJ is conjugate orthogonal. The optimization problem can be split into several parts individually. In every part, we just need to solve a simply two-order optimization problem to find alpha I. So our algorithm is that by Schmidt orthogonalization finding a new QJ, and calculate a new alpha. Lucky Schmidt orthogonalization is only related to the last calculated Q, we just need to save 3 parameters during the iteration. Finally, Ci equals alpha IQI. Here are the results of our algorithm, as the images show from B to D. With the increasing of the support radius, non-uniformly sampled parts become continuous and smooth. At the same time, the details could still reserve with the same parameters when compared with B-spline implicit PIA, such as hair. As the images shows from B to D top. With the increasing of the support radius, missing data regions will be patched, and details could still reserve. Noisy data also can be denoised, after using a regular matrix, and several iteration times. Finally, we conclude the main technical contributions as follows. 1. An implicit geometric iterative scheme based on locally supported radial basis functions is constructed, with the quasi-interpolation results as initial values. 2. The convergence of the iterative process is analyzed theoretically. 3. A geometric iterative acceleration algorithm based on conjugate gradient direction is provided, as well as its convergence analysis. This method is simple to be implemented and easy to be parallelized. Thank you for your attention.